So let's go ahead and find the exact area between the graphs of e to the x plus 1 and y equals x between 0 and 2. So first we'll take a look at the graph. Here's e to the x plus 1. Now remember what the integral gives us from 0 to 2. That gives us the area underneath the e to the x plus 1 and above the x-axis. Well, okay, let's add the graph of y equals x to our plot. And remember that doing the integral from 0 to 2 will give us the area under x as well. So you can see that in red here. Well, we want the area between the two curves. So what we can do is take the area that's under e to the x plus 1 and subtract out the area that's under x, and that'll give us the area in between. Here's what that integral would look like. So from 0 to 2, we have the integral to give us the area under e to the x plus 1, and then we're going to subtract out the area under x. Well, since these two integrals have the same limit, we can rewrite them as a single integral. Notice that it's the function that was on top minus the function that was on bottom in order to find our integral. That's always going to be the case. Now, one interesting twist, we want to find the exact area between these two graphs, x plus 1 and 7 minus x, between 0 and 4. So here's those two graphs graphed together, and if we shade in our area, notice that the function that's on top switches at their point of intersection. So what we're going to have to do is actually two separate integrals. One of them is going to go from 0 to their intersection point, which in this case occurs at 3, and then the other one's going to go from 3 to 4. And we have to switch which function's on top, because it's 7 minus x here, and it's x plus 1 over here. So the integral to calculate this area is going to look like the following. We're going to go from 0 to 3 with 7 minus x on top and x plus 1 on bottom, subtracting them, and then from 3 to 4 with x minus 1 on top and then subtracting out 7 minus x. So we get the following two integrals. Something kind of interesting to notice from 0 to 3 it's 6 minus 2x, and from 3 to 4 it's 2x minus 6. They're always going to look like opposites as far as the integrand when you have a case where you have to split them at some point of intersection. So remember, it's always the function on top minus the function on bottom. One last thing to show you is if we wanted to find the exact area enclosed by two graphs, for instance x squared and 2 minus x squared, notice in this case we weren't given limits of integration like we were in the last two. Well, let's take a look at the plot. Notice that there actually is an area enclosed by the two graphs. So if we shade that in, we're actually going to get our limits of integration by looking at the intersection points between the two graphs. Now these two happen to intersect at -1 and 1, and we only care about the x values because those will be our limits of integration. So the definite integral calculating this area is going to look like the following. -1 to 1, function on top, 2 minus x squared, minus the function on bottom, x squared, and we can simplify a little bit in this case.